am also a sophomore from Hillsborough. Um, so let's see. I enjoy math as much as the rest of us. I've tutored math in the past, so that's basically all of us, I suppose.
Yeah. Yeah, great. Let's just say one thing we like to do outside of math. Oh, by the way, all of us, we were all the 2019 National Math Counts team from Oregon, which placed seventh. And many of us have qualified for tests like Amy and USAGMO. So we all love doing math, and we've done math competitions, and we really want to pass it on. So yeah, one thing I like doing outside of math is playing basketball and following the NBA. So that restarted recently, which I'm pretty excited about. David?
One thing I also like doing outside of math is wrestling, and I'm on Sunset's varsity wrestling team. So yeah.
Yes, I mentioned a couple things just a moment ago. That one other thing, more specifically, I played a saxophone.
Let's see. I'm interested in chemistry, I suppose, outside of math. Um,
And the four of us also want to get to know all of you guys. So can everybody put their favorite thing to do outside of math in the chat?
Yeah, just put it in the chat. Chess, basketball. A lot of basketball. Nice. Physics, programming. Cool. Yeah, this is great. So let's definitely get to know each other more as we continue classes. But for now, let's get started. So as we said in the advertising for this class is to teach is to help people prepare for math competitions, specifically at the level of contests like AMC 10, definitely a lot of AMC 10 preparation. Early AIME, which is the test after the AMC 10. Also, if you've heard of AMC 8, this might help with some of the harder problems there, although many of the problems in the AMC 8 are easier than those in the AMC 10 and AIME. And also math counts. This will definitely help a lot for state and national math counts. All of us have done it, and we feel like we've put together a really great curriculum, which would help for people preparing for math counts. So yeah, math counts, AMC 10, not too much of the really hard computational problems, but more at the middle level. So yeah, today we'll be starting with the topic divisibility and prime factorization, so number theory. Definitely appears a lot in math competitions. And yeah, so Nivid, you want to take it away?
Yeah, sure. I want to share my screen, so everybody should be able to see my screen right about now. All right, so today we're gonna start off with some basic definitions, and these definitions are kind of just to get everybody into the spirit of numbers and just that everybody understands what we're talking about later on more, and then also so that we all are on the same page with everything we talk about. So the first definition is that when we say A divides B, or um, when we write it like on the slide, it means that B divided by A is an integer. So that's the first definition. Our second definition is prime factorization of numbers. And this is a unique way to write it where we put everything into prime numbers. So if we have a number n, we write n as a product of not necessarily distinct primes. So for example, 20 factorial would be 2 squared times 5. Another example is that 24 factorial would be 2 cubed times 3. And we can also write it the second way where we have any k, and because k to the power of 0 is equal to 1, so that doesn't affect our prime factorization. Our next definition is the greatest common divisor. And the greatest common divisor of two numbers a and b is the largest number that divides both a and b. So for example, the greatest common divisor of 42 and 70 is 14, and this is because 14 is the biggest number that goes into both 42 and 70. The least common multiple, or LCM, is of two numbers a and b, is the least number that is a multiple of both a and b. So for example, the least common multiple of 42 and 70 is 210, and this is because both 42 and 70 evenly divide 210. And another definition we have is that when we say two numbers a and b are relatively prime or co-prime, it means that they share no common divisors. So in other words, this means that the greatest common divisor of a and b is equal to 1. So an example of this would be the numbers, let's say 20 and 7. So 20 by itself isn't prime, but 20 and 7 are relatively prime because their greatest common divisor is the number 1. So why is prime factorization useful? Um, well, we use prime factorizations to compute the greatest common divisor and the least common divisor. And the least common divisor and greatest common divisor are used a lot in math, and we'll get into their uses a little bit later. So in order to prime factorize a number, it's pretty simple. So suppose the exponents of p and the prime factorizations of a and b are p e to the e1 and p e2, respectively. And then the exponent of p in the greatest common denominator of a and b is p to the power of the smaller number e1 or e2. So in other words, all this is saying is that if we have two numbers a and b, and there's a prime number that goes into both numbers, we look at the exponents and we take the smaller exponent, and then that's going to be the exponent of the factor in our greatest common divisor. So for example, the greatest common divisor of 2 to the 5th times 3 to the 7th times 7 to the 3rd and 2 to the 1st times 3 to the 9th times 5 is 2 to the 1st times 3 to the 7th. Because if we look at it, well, 2 is common in both numbers, and the smaller exponent is the 1, so we put 2 to the 1 in our final answer, you could say. And then 3 is common in both, and the smaller exponent or the smaller power is the 7, so the other is 3 to the 7. And 7 and 5 only appear in one of the numbers, so that's why it doesn't appear in the greatest common divisor. On the other hand, when we look at the least common multiple, um, we uh, we look at the maximum exponent of the two numbers. So we look at the same example, except now we're finding the least common multiple. Well, first we look at the 2's, and the higher exponent is the number 5, so we get 2 to the 5th. And then we look at the 3's, and the higher exponent there is the number 9, so the 9 goes over. And then we look at the number 5, and on the first term, we have 5 to the 0th, and on the second term, we have 5 to the 1st. So that's why the 5 to the 1st carries over onto our least common multiple. And then we look at the factor 7, and for 7, there's 7 to the 3rd and 7 to the 0th power, so 7 to the 3rd carries on. All right.
All right. Yeah, so thanks for the quick introduction to all the prime factorization stuff, Nivid. Should I share my screen now?
Sure.
Okay.
Yeah, if you could stop a bit, we've had some requests to go a bit slower. So if you could just.
Sure, yeah.
Yeah.
I guess I'll just briefly go over what Nivid covered in this.
Yeah, sure.
Okay. Yeah, so like Nivid said, the greatest common divisor of two numbers is the biggest number that is a divisor of both of them. So remember, a divisor is a number that we said it in the definitions. It's a number that goes in evenly, essentially. So if we want to think about the prime factorization, then the prime factorization is basically a way to break down numbers into these indivisible blocks called primes. And whenever you want to find the prime, the greatest common divisor, then let's just go to this example right here. By the way, can you guys see my mouse or not? Like where I'm pointing?
Yes.
I can see.
Okay, cool. Yeah. So when we have something like 2 to the 5th times 3 to the 7th times 7 to the 3, and 2 to the 1 times 3 to the 9th times 5. So these are two prime factorizations of two numbers, because these numbers down here, 2, 3, and 7 are prime numbers, and 2, 3, and 5 are prime numbers. So this cannot be broken down any further into primes. The 2 to the 5th is saying that there's 5 2s, this 3 to the 7 is saying that there's 7 3s, and so on. So if we want to find the greatest common divisor, then, well, surely 2 to the 1 goes into both of these numbers, this number right here and this number right here, because 2 to the 1, it divides this part, and 2 to the 1 divides 2 to the 5th. So it divides this entire number. Does 2 squared divide both of these numbers? Remember, the greatest common divisor, it has to divide both of the numbers. So we have to check for each prime if it's dividing both of the numbers. So 2 to the 2, let's check. 2 to the 2, it goes into this for sure, because 2 to the 2 divides 2 to the 5. But 2 to the 2 does not divide this, because 2 to the 2, it certainly doesn't go into any of the primes here, 3 or 5, but 2 to the 2 is not a divisor of 2 to the 1. So that means that the highest prime, the highest exponent of 2, exponent is just how many 2's there are, the total number of 2's in the prime factorization of the greatest common divisor is just 1. We can't have two 2's because there's only one 2 over here, and if we have 1 2, then it works. So 2 to the 1. Similarly, for 3 to the 7, there's 7 3's here and 9 3's here. So if we take, so 3 to the 7 divides both of these, but 3 to the 8th does not divide both of these. So that means that the exponent of 3 is 3 to the 7. Basically, what prime factorizations help us with is we can just go prime by prime, 2, 3, 5, 7, and so on, and just check for both of these numbers, this first number and the second number, what's the highest exponent, what's the total number of those primes we can fit in that will divide both of these. So we look at a prime 2, we checked 3, now let's check 5. Well, 5 doesn't even divide this, so any exponent of 5 surely cannot divide this, which means that 5 cannot divide both, which means there won't be any 5 in the greatest common divisor. Similarly, even though 7 divides the first one, it does not divide the second one, which means that 7 will not appear in the greatest common divisor. Obviously, any primes bigger than 7, they don't divide either, so they're not going to be part of the greatest common divisor. So basically the idea, just to recap, is we go prime by prime. This theorem is just a formal way to say it. But if you want to think about it, using this example, we go prime by prime, 2, 3, 5, 7. These are the number of, there's 5 2's here, and there's 1 2 here, which means the greatest common divisor will have 1, 2. Similarly, the least common multiple is very similar. Instead of trying to find the greatest common divisor, we want to find the number that is a multiple of both and is the smallest. So again, we go prime by prime. For 2 to the 5, let's see, does 2 squared can 2 squared be a multiple of this? Well, 2 squared is certainly not a multiple of this. And the idea is that if we go prime by prime, we can't have 2 squared in the prime factorization of the LCM, because then there's 5 2's here, but there's 1 2 here. So if we have 2 to the 6th or 2 to the 10, then 2 to the 10 or 2 to the 1000, then that would work. But that's not the least possible. For the least possible, we can have 2 to the 5th, because 2 to the 5th is a multiple of 2 to the 5 and of 2 to the 1. Similarly, go to the next prime. We take whichever one is bigger, because there's 7 3's here and 9 3's here. So we want to be able to fit all of them in. So the least common multiple will have 3 to the 9. Similarly, for 5, there's 0 5's here, but there's 1 5 here. So we're going to have 1 5 in the LCM. For 7, there's 3 7's here, but 0 7's here. So it's going to have 3 7's. So for the LCM, you take the bigger one for each prime, and for the GCD, you take the smaller one. That's what we were trying to say in the theorem up here. So It's the min, which is the smaller, and max, which is the bigger. I know this might be a little confusing if you've never seen this before, so go back, read the slides. We're also going to publish a handout after the class on the website, and you can read that in more detail if you're confused. But that's how GCDs and LCMs are benefited by the prime factorization. If I just told you find the greatest common divisor of 1001 and 2103, well, there'd be no way to do it, at least systematically. But with the prime factorization, you can just go prime by prime. So that's a process. So that's what we're trying to cover here. Now, that's why prime factorizations are useful, like I said. Another way to do it is to find the number of divisors of a number. So let's do a quick example first. Can everybody spend a minute and figure out how many factors, how many divisors does the number 12 have? So just, I'll give everybody 30 seconds. Type it into the chat. How many divisors does 12 have? And I actually can't see the chat. So can you guys, maybe one of you three, let me know what people are saying?
It is.
Yeah, they're all getting it. So.
6.
6. Okay, yeah, great. And I'm guessing the way you all are doing that is by saying, okay, 1 divides it, 2 divides it, 3 divides it, 4 divides it, 5 does not divide 12, 6 divides 12, that's 6, and 12 divides. So there's actually, exactly, 1, 2, 3, 4, 6, and 12. That's 6. But what if I told you find the number of divisors of 2 to the 10 times 3 to the 13th times 5 to the 7? Well, there'd be no way to do it. That number is massive. It's like a billion. How would you do it? This is what this theorem that you're able to see on the board is helping with. So basically the idea is whenever we want to think about a number, we can just write its prime factorization, which is hard. Let's say I just tell you like 2,100,000 or something like that. It's hard to write down the prime factorization. But once you have that down, you can deduce a lot of things. Things like greatest common divisors between it and other numbers. And one other thing we can do now is find a systematic way to find the number of divisors it has. So 2 to the, let's say in general, it's P1, so P1, P2, all the way till Pk are primes. P1 to the E1, P2 to the E2, all the way till P sub k to the E to the k. So for example, this could be going back above, maybe it's 2 squared times 3 cubed. Or in the example of 12, it'd be 2 squared times 3. Then the number of divisors, there's a formula, which is you add 1 to each of the exponents and you multiply them all together. So this isn't supposed to make sense at first. This seems really magical, right? Like, let's say I just told you find the number of factors that 2 to the 10 times 3 to the 3 has. I mean, it'd be really hard, but apparently it's just, so 2 to the 10 and 3 to the 3, so 11 times 4. Apparently there's 44 factors. So let's go through why this is true. This theorem demonstrates why prime factorizations are so useful. Okay. So yeah, let's first define some notation. For n, let tau, this little t symbol, it's a Greek symbol, it's called tau. Let tau of n be the number of divisors of n. So our goal is to find tau of p, p1 to the e1, p2 to the e2, all those with pk to the ek. That's our goal. So first, let's think about a simple case. Consider the number 11. How many factors does it have? It only has 2. Well, because it's prime. The definition of a prime number is the only factors it has are 1 and itself. So tau of p is 2 because that's the number of divisors it has. Similarly, let's say I said, how many factors, why don't people type this in the chat again? How many factors does 11 to the power of 3 have? Remember, 11 is a prime. Yeah, I can't see the chat again, so just...
4.
Are people saying 4?
Yes.
All right, yeah. 11 to the 3 does have 4 factors, and those are 1, 11, 11 squared, and 11 cubed. So those are 4. So you didn't have to multiply out 11 to the 3 and find all numbers that divide. You can just say that because 11 is a prime number. So p to the k, well, in the example I just said, p is 11 and k is 3. So tau of 11 to the 3 is 4. In general, tau of 11 of p to the k is k plus 1, because there's the factors of p to the k, where p is a prime, are 1, p squared, p cubed, all the way till p to the k. So that's p to the 0, p to the 1, all the way till p to the k, and there's k plus 1 of those. So this solves it for a very simple case of a prime power. A prime power is just a number that's a prime number raised to a power, and that has k plus 1. Well, what if it's not a prime power? So let's go to an example of 24. Well, using the prime factorization, there's actually a pretty systematic way to write down the divisors. So the prime factorization of 24 is 2 cubed times 3 squared. Can people, actually, let's do this again. Last time we're going to do this, but write down all the factors of 24, not just how many, which ones. And I want to see what sort of systematic way people are able to write those down. So take a minute and write down all the factors of 24 in the chat. Not just how many, write down the entire list. What we're planning to do here is, instead of just finding the number of divisors, we can actually classify all divisors, and then counting them will be easy. Has anybody done it?
Yeah, lots of people have one. We have 1, 2, 3, 4, 6, 8, 12, and 24.
Wait, sorry. I mean, 24. That's 2 cubed times 3, right? Not 2 cubed times 3 squared.
Yeah, that's my bad.
Whoops.
It should be, instead of 24, this should say 72. So 2 cubed times 3 squared is 72. Yeah, so like people said, obviously you can modify this for 72. The factors would be, in terms of the prime factorization, 2 to the 0 times 3 to the 0. Well, that's just 1. 1 divides any number. 2 to the 1 times 3 to the 0, that's 2. That also divides 72. 2 squared times 3 to 0. So what we're trying to do with this grid is say all divisors which have 3 to the 0 in their prime factorization. So any divisor of 72 must be of the form 2 to the something times 3 to the something. Because it can't have, for example, 5 to the something or 7 to the something, because 5 doesn't divide 72, 7 doesn't divide 72, and so on. So we'd have to have 2 to the something times 3 to the something dividing 72. And in particular, the numbers we can have are 2 to the 0 times 3 to the 0, 2 to the 1 times 3 to the 0, 2 to the 2 times 3 to the 0, 2 to the 3 times 3 to the 0, and we cannot have 2 to the 4 times 3 to the 0, because 2 to the 4, there's not enough 2's here. 2 to the 4 can't divide 72. So this row, where we're just fixing it at 3 to the 0, is going to be just 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Now if we say, okay, well, what if the divisor is a multiple of 3? Well, then which numbers work? So we have 3 to the 1, and then the numbers that divide 72 are 2 to the 0 times 3 to the 1 all the way till 2 to the 3 times 2 to the 1. Again, we can't have 2 to the 4 times 3 to the 1, because 2 to the 4 does not divide, there's not enough 2's. So we go from 2 to the 0 all the way up to 2 to the 3. Finally, 3 to 0, we fixed 3 to the 0, we fixed 3 to the 1, now 3 to the 2. Again, 2 to the 0 all the way up to 2 cubed. So in total, this gives a really systematic way. What I'm trying to emphasize is why this is useful. The reason this is useful is we've been able to classify every single divisor of 72 using the prime factorization. So they're just going to have 2's and 3's, and the exponent of 2 is going to go all the way till 0 to 3, because there's 3 here, and we can't have more 2's than that. And the exponent of 3 is going to go all the way till 0 to 2, because we can't have more than 2 3's. Does that make sense to people? Just thumbs up or thumbs down. I think that's a feature in Zoom. We're gonna take all the twos up from 2 to the 0 to 2 to the 3, and threes from 0 to 2. Uh, does raising hand mean you have a question? If so, you can speak or type in the chat.
What does the T mean again in front of the N?
Uh, T just are you asking for this right here?
Yes.
That's just a function which is going to say like how many divisors it has. So like tau of n, the way you say it is tau, it looks like a T, yeah. It's just the number of divisors. So tau of a number just tells you how many divisors it has. We're trying to compute a formula for tau of n. It's just a function. So I hope that explanation makes sense. And so this gives a systematic way to find the divisors of, say, 72. Now let's generalize. Like I said, let's just do some recap. Any divisor of 2 cubed times 3 squared is of the form 2 to the a, 3 to the b, for some a from 0 to 3 and b from 0 to 2. So we can't have any anything other than 2s and 3s. And for 2s, we can have up till 3, and for b's, we can have up till 2, because there's only 3 2s and 2 3s. So now let's get to the counting. What we've done so far is classified every single possible divisor of 2 cubed times 3 squared. Now, to count it, we need to just count how many ways there are to choose an A and choose a B in these ranges. Well, for an A, if we go back to this grid, maybe I can show both of these at the same time. Yeah. Well, look at this grid. It's three columns. It's 3 blocks high and 4 blocks wide, which means there's 12 numbers in this grid. And that makes sense because every grid corresponds to a pair A comma B, where the divisor is 2 to the A times 3 to the B. So there's 4 choices for A, which are 0, 1, 2, or 3, and there's 3 choices for B, which are 0, 1, and 2. And the reason we're multiplying those is because we can think about putting them in a grid, like is done up here. And the total number of cells is the total number of divisors, because each number in a cell corresponds to a divisor. So for example, this number right here in a cell, random cell, 2 squared times 3 to the 1, well, that divides 2 cubed times 3 squared, because 2 squared times 3 to the 1 is 12, and 2 cubed times 3 squared is 72. 12 divides 72. And the reason for that is because the exponent of 2 is less than the exponent of 2 here, and the exponent of 3 is less than the exponent of 3 here. Okay? So for 72, we were able to say, okay, it's 4 blocks wide, 3 blocks high. That means there's 12 divisors. Now, can we generalize this to, so far what we've done is for a prime power, p to the k, that's just a number like 11 cubed. We've also done it for a number like, which has 2 prime powers in it, like 2 cubed times 3 squared. So to generalize, in general, let's do it for 2 to the m times 3 to the n, for any m and n. The process is very similar. Again, any divisor is going to be of the form 2 to the a times 3 to the b. Actually, before we do this, did everybody understand how we counted it? Thumbs up, chat, and any just way to communicate that. Or if you have any questions. Any questions about, this part is pretty tricky. Does it make sense to people? How we were able to get from classifying all the divisors to counting how many there are. Wait, are people saying yes?
Yes, they are.
In the chat?
Yes.
Okay. Yeah, if anybody has any questions, let's just wait. Like, I'm going to wait for 15 seconds. Just any questions? Feel free to speak or type in the chat. All right. No questions? Yeah, sorry.
Marul asks, what do you mean by E?
E.
Could you clarify? The exponent.
Yes. E is the E1, E2, E all the way to EK. That's just notation for the exponent of each prime. So for example, 2 cubed times 3 squared, well, the exponent of 2 is 3, the exponent of 3 is 2. So the e's are just denoting the exponents, how many of each prime we have. Okay. Yeah, and also if anybody ever has any questions on anything, feel free to email at the pacificmathsociation@gmail.com. We'll be happy to answer any questions if you have questions offline or anything else. But right now, any questions in the chat or speak? All right. So in general, if we're computing divisors of 2 to the m times 3 to the n, so general exponents, well, similarly, it has to be of the form, it has to have some 2's and it has to have some 3's, any divisor. Well, it can't have any 5's, it can't have any 7's, because it's dividing 2 to the m times 3 to the n. So the options for the number of 2's, well, the number of 2's can be anything from 0 till m. So that's 2 to the m, since there's m 2's in the number, and there can be any from 0 to n 3's in the divisor. So we have to choose a value for a and a value for b. So for example, 2 to the 1 times 3 to the 1 would work if m and n are at least 1, because 2 to the 1 times 3 to the 1 divides 2 to the m times 3 to the n. So there's m plus 1 choices for the number of 2's we can take, and n plus 1 choices for the number of 3's we can take. And any combination of these works. So for example, 2 to the 5 times 7 to the 1 divides 2 to the 1000 times 3 to the, let me say that again. 2 to the 2 times 3 to the 5 divides 2 to the 1000 times 3 to the 1000. Well, because 2 is less than 1000 and the other exponent, they're both less than 1000. So any combination, my point is any combination works. And the number of ways to choose that, it's just m plus 1 times n plus 1. In general, we can say that if we're trying to choose any divisor of this number, p1 to the e1, p to the e2, a general prime factorization, well, you just have to choose the exponent of the divisor for p1 to be anything between 0 and e1. There's e1 plus 1 choices there. For e2, we have to go from 0 to e2, so there's e2 plus 1 choices. And similarly, we can keep going. And multiplying those all together, well, because we can choose one from each sort of like bucket for each prime, and any combination works, that's why we multiply. And the total number of divisors is this. And in general, we can think like, I think this grid, the grid we were able to, let me get back to it. For 72, there was one, yeah, this grid right here. So in general, when we have more than 2 different primes, it'd sort of be a 3D grid where each axis is representing a different prime. And that's just a way to visualize it, but you're sort of trying to find the number of cells in that and you multiply it all together. So again, in general, there's e1 plus 1 choices for the exponent of p1 and so on. So you multiply those together, and this gives a general formula. So going back to the statement of the theorem, now that we've covered the proof of this, now you can tell me how many divisors 2 to the 1000 times 3 to the 1000 has. Well, it simply has 1001 times 1001, because there's 1001 ways to choose the number of 2's and 1001 ways to choose the number of 3's, and then you multiply those together. So this gives a general formula and really harnesses the power, of the prime factorization. All right. Does that make sense to everyone? If not, if yes, since this is a math competition class, a lot of what we're going to be covering is theory, as well as problems that have appeared in the past in previous contests, and we can see how to apply the techniques we've learned to solve those. The goal is to help you get better at them. So here's our first example. Why don't you guys actually never take it away? So everybody just spend a couple minutes reading the example, work it out on your own. We'll give you 2 or 3 minutes, and then yeah, Nivid will cover how to do it.
Yeah, we'll give everybody a few minutes to do this, and then we'll get started on the walkthrough.
I'm gonna stop screen sharing for a minute, so you might not see the problem, but Nivet will start screen sharing. One second. Nivet, do you want to screen share the same slide? Yeah, great. So yeah, just keep working on the problem for about a minute, and then we'll see here.
All right, it's been a few minutes, and I've been seeing some answers in the chat. So we can get started on kind of the solution for this problem. So first, for this problem, we'd simply start out by finding kind of the smallest factors of this number. So 2 trillion, 14 billion is a really big number. So we can start out by looking at what are the smallest divisors. And of course, this is kind of counterintuitive because it's asking what's the largest divisor. But when we have any divisor, divisors come in pairs. So for example, this number is 2 trillion 14 billion, and if we have the divisor 1, this comes in a pair with 2 trillion 14 billion. If we have the divisor 2, this comes in a pair with half of 2 trillion 14 billion. And so on, we can make pairs of everything besides the square root of this number, and one will be a smaller number, and the other one will be the number we had to multiply to get our final number. So if we look at this, first we find the smallest divisors, which are 1, 2, 4, 5, and 8. So these are the 5 smallest divisors. So we want to find the 5 biggest divisors of 2 trillion 14 billion. Then we had to divide 2 trillion 14 billion by these 5 smallest divisors. So since the fifth smallest divisor is the number 8, we had to divide 2 trillion 14 billion by 8, and this gives us the answer C, 251 billion 750 million. Does that make sense?
Want to just go over that again, Nivet, but repeating 2 trillion 14 billion, just replace that with n.
All right, yeah, sure. So I'll go over this again, except replace 2 trillion 14 billion with the number n, just to make it a little easier. So for all divisors of n, we have, let's say a is a divisor of n, then we have, a comes in pairs. We have the number a, and we have n over a, and a is on the smaller side, and n over a is on the bigger side, you could say. So if we want to find the fifth largest divisor, we can start by finding the 5 smallest divisors of n, and in this case they were 1, 2, 4, 5, and 8. And then using this, we can find the 5 biggest ones, fifth biggest one by finding n over 2, n over 4, n over 5, and n over 8. And then n over 8 must be the fifth biggest one because we're dividing n by kind of the 5 smallest numbers.
Yeah, did that make sense to everybody? Just yeah, any questions, put them in the chat. All right.
So it's basically dividing like the five smallest divisors and see which one can divide them all. Is that how you do it?
Because divisors come in pairs, that fifth smallest divisor is going to correspond to the fifth largest divisor, basically.
Yeah, exactly what Alan said. The fifth smallest divisor times the fifth biggest divisor is going to be n. The reason for that is Niv and Alan said, divisors come in pairs. So the biggest and smallest, when you multiply them, the number, because the biggest is simply n, smallest is 1. Similarly, the second smallest is n over 2, the second biggest is n over 2, second smallest is 2. So those also multiply to n. So the fifth smallest times the fifth biggest is also n. And it's really easy to compute the fifth smallest. It's hard to compute the fifth biggest, but the fifth smallest is simply 8, because 1, 2, 4, 5 are the smaller ones, which means the fifth biggest is n over 8. And then you can compute that to be c.
Sorry, my thing lagged out for the part when you said the fifth smallest and fifth biggest, you get what?
Just read the slides after the class. But what I said is that fifth smallest times fifth biggest is going to be the entire number. But yeah, we're definitely going to be uploading the slides and handout after the class. So just if you miss anything, just review it from there.
Okay, thank you.
Yeah. Okay, so I think that example made sense. Let's move on to the next example. You want to stop screen sharing now? All right. All right, do people see this problem?
Yeah.
Okay, so again, take 2 minutes, try to solve it. The hint for this is that this really looks like an algebra problem, and there is a way to solve it using algebraic techniques, but try to think about a really slick way to solve it involving the answer choices that you're given. So just try to apply some number theory, and there is an easier solution. So that's the hint. But yeah, take 2 minutes and then we'll go over it. Also, yeah, I made the chat send to the hosts only so that people get less distracted. FYI. I'm not sure if it sends to the co-hosts, but we can try to figure that out next time. Just so it's less distracting, people can see each other's messages.
We have a question. Where will the recording be for the class?
We will be uploading the recordings to the website after classes sometime during the week. But yeah, if you miss something, you can definitely go over the recordings after the class. Again, the solution, this is more of a trick question, so try to use number theoretic methods instead of algebraic manipulations. There's a really quick way with number theory. Okay, I think it's been long enough, and let's go over the solution. So the question is, we have relatively prime integers, remember, relatively prime means um, that the GCD is 1. And we're given relatively prime integers with a bigger than b, satisfying this equation. So a cubed minus b cubed over a minus b cubed is 73 over 3. What is a minus b? So there is a way to do this using algebra, like I said, which is to sort of cross multiply it and expand. But on the contest, that might take a bit long. And there is a way to, and you want to figure out which answer choice is correct. So we're going to be using the answer choices. So like I said, there's a tricky way to get the answer on the contest. So cross multiplying, we get 3 times a cubed minus b cubed equals 73 times a minus b cubed. Well, 3 divides the left-hand side. 3 divides 3 times something, which means 3 also divides the right-hand side. So 3 divides 73 times a minus b cubed. And notice that 73 is not a multiple of 3. 73 is a prime number, actually. Well, it's not a multiple of 3, which means that if 3 divides a not a multiple of 3 times something else, well, 3 must divide a minus b cubed. So then what we get? Yeah, since 3 and 73 are co-prime, 3 actually just divides a minus b cubed. And again, since 3 is prime, well, if 3 divides something cubed, then 3 has to divide that thing itself. For example, 3 does not divide 17. So that means 3 cannot divide 17 cubed. There can't be any factors of 3 in 17 cubed if there are none in 17. And if 3 does divide a number, say 3 divides 6, well, then 3 also divides 6 cubed. So the fact that 3 divides a minus b cubed means that 3 actually divides a minus b. And what do you know? If you look at the answer choices, only one of them is a multiple of 3, and that's C. So we got that 3 divides a minus b, and 3 is the only multiple. Does that make sense to everybody? So this is just a tricky way if you're given the answer choices. Without the answer choices, this would be a good algebra problem. But this problem really tests if you understand, like 3 divides this expression here, then reducing that to 3 actually just dividing this. Does that make sense? Just thumbs up, thumbs down, anything in the chat. All right, cool. Nevid, you want to take the next example? I'll start screen sharing.
Yeah, so for this example, we'll give everybody a few minutes to work on it, and then we'll go through the walkthrough.
Wait, what are tuples?
So 7 tuples just means 7 integers A, B, C, D, E, F, and G that are in that order and that satisfy the conditions below.
Yeah, a tuple is just a list of numbers.
All right, I'll give everybody one more minute and then we're going to start working on the problem together.
Mm.
Okay, you want to start,
All
Nimin?
right. Yep. We can get started on the solution now.
And
So,
just one thing before we start, Nimin. Class ends in 7 minutes at 6 o'clock PST. So just letting you guys know.
all right. So to first get started with this, first we want to kind of look at all the numbers and see what numbers go together. So if we look at this, first we'll notice that C must divide 70 and C must also divide 71. So this means that C must divide the greatest common divisor of 70 and 71. So the greatest common divisor of 70 and 71 are both equal to 1, is equal to 1, so C must be equal to 1. So this simplifies our equations a little bit, and we can do the same thing with the letter E. So we notice that E is a divisor of the number 71, and E is a divisor of the number 72. So E must be a divisor of the greatest common divisible of 71 and 72, and that is equal to 1. So E must also be equal to 1. So after those two equations, we simplify this a little bit. So now the second equation just becomes D is equal to 71 because C and E are both equal to 1, so D must be equal to 71. And our first equation becomes AB is equal to 70, and 70 is 2 times 5 times 7, so it has 8 factors. And this means that there's 8 choices for A and B. Because like we talked about earlier, all divisors come in pairs. So we can pick any of these 8 factors for the letter A, and then B must be um, 70 divided by whatever A is. So there's 8 choices for A, B. And looking at this, we can also use the same logic with the third equation. So the third equation becomes FG, and FG is equal to 72, which is also in prime factorization, uh, 2 cubed times 3 squared. And this means that it has 12 factors. So there are 12 choices for F and G because as we know, divisors come in pairs. So whatever we pick for F forces G to be 72 divided by F. And since there's 8 choices for A and B, and there's 12 choices for F and G, and there's one choice for all of our other numbers, the answer must be 96. And there's 96 7 tuples of positive integers. So does this make sense, everybody?
Yes.
Yeah, and any questions, just put them in the chat or feel free to speak. Um, yeah, one thing I realized that might be confusing, the way we got that C divides 70 and C divides 71 in the beginning is because if you look at the equation, it says ABC equals 70, which means that C divides A times B times C because A and B are some numbers. So C divides the product, and from there you have C divides ABC, and ABC is just 70, so C divides 70. Similarly, from the second equation, C divides C times D times E, which is 71, so C divides 71. If C divides 70 and C divides 71, well, then it has to divide their greatest common divisor because it divides both numbers. And you can't have any number dividing 70 and 71 except for 1. Similarly, E appears in both the equations for 71 and 72, which means C divides their GCD, which is 1. And then from there, you can reduce it to just two variables in each equation. And then, like Nivid said, since their prime numbers come in factors, you can just choose one of them. And the number of factors, well, we did that in an earlier in the walkthrough, and then from there you just multiply those and get your answer. So the idea is that most numbers get determined just from the fact that what I mean is that C gets determined and E gets determined because C divides 70, 71, E divides 71 and 72. And from there, the equations become a lot simpler. Yeah, so if this example was confusing, I know we had to rush it a bit because class is about to end. Then we'll be uploading the handout, which has more explanation, and you can also go online and try and see if you're still confused, you can email or go online. But yeah, so I think we won't have time to go over the next example, but any questions for this one or anything before? The slideshow and handout will be uploaded to the website. But any questions?
Wait, I still don't get how A times B has 12 choices.
Well, A and B only have 8 choices because A times B is equal to 70 because we found that C is equal to 1. So since A times B is equal to 70, and if we look at it, well, 70 is equal to 2 times 5 times 7, which means that it has 8 factors. So since there's 8 choices for A, and B always has to be kind of the opposite of A, or 70 divided by A, then there's 8 choices for A and B. So I think you might have got confused because there's 12 choices for F and G, but 8 for A and B.
For A and B.
And the handout will go over these walkthroughs, and the handout will also have 9 or 10 problems that you can work on at home for homework. It's not due or you don't have to submit anything, obviously, but it's for your own practice. And yeah, so the handout will be uploaded with the walkthroughs and more example problems. And it also includes the last problem we didn't have time to go over. But yeah, I think we're gonna end now. If anybody has any questions, email at the email you got the Zoom link from. I'll type it again: Pacific Math Association at gmail.com. I might have misspelled it, but Pacific Math Association at gmail.com. Email with any questions or anything else. Recording.
Uga chaga, uga chaga.
Oh, sorry. Will be uploaded, and yeah, thank you everybody for attending.
I have a question.
Yeah, go ahead.
When is the handout gonna be on the site?
The handout and slides will be uploaded within today or tomorrow.
Okay, thanks.
Okay, thank you everybody for attending. Next class will be next week, and yeah, next week same Zoom link. Thank you. See
Bye.
you.
See you all next week.
Thank you. Bye.
Same
Bye.
Zoom link?
See you.
you. Bye.
Thank you.
Thank
Bye.
Bye.
Thank you.
Thank
Bye.
you.
The same Zoom link?
We'll hang
Okay.
around.
Bye.
If anybody has questions.
Thank you so much for the course. Bye.
Thank you.
No, thank you for coming.
So basically, we have to go check the same email every week.
We'll send reminders every week, but it's going to be the same Zoom link. But we'll send reminders every week.
Okay. Thank you. Bye.
So the Zoom meetings are only on Mondays?
Yeah, every Monday from 5 to 6 p.m. Okay. Basically everybody's gone. Should I close the meeting, guys?
Yeah, that's fine.
Yeah, I think that sounds good.
Can you guys head over to Discord for a sec?
Okay.
Sure.